Hello everyone, welcome to Practical Mechanics. I'm Mohsen. Today's video is about to look at the thin walled cylindrical pressure vessels and look at ASME code and also draw Mohr Cicle for this condition and see that what stress is actually governing the design of thin walled pressure vessels, especially cylindrical thin walled pressure vessels. Let's start it. Consider a cylindrical pressure vessels. These cylindrical pressure vessels is actually produced with flat end, dish ends, spherical ends, or head, and spherical, conical head, or conical heads. Then, if it is subjected to internal pressure, the stresses that grow because the shell is called thin. Thin shell means that if the divided diameter to thickness, it must be less than 20. This is the standard actually limit. How to consider vessels as a thin or how consider it as a thin. They are completely different stress formula and distribution of stress. Okay, this pressure vessels is thin and we have only stresses in longitudinal directions, which we call them sigma longitudinal, and circumferential stresses that we consider hoop stress. Another name is tangential stress. Then we want to calculate them. If we cut an imaginary cut for this cylinder, see what we have. This is the plate that we cut it. Consider our mean radius, consider thickness T, and that's the whole cylinder under pressure PI. Also pressure in the other for the shell, internal shell, and we don't consider them. Why? Because in the y direction or any other direction except x, they neutralize each other. The only force that we have due to pressure is in x that must be balanced with this internal pressure or internal reaction. Let's find out. I told you we have different types of head, but the pressure act on that. The area that is cut is called projected area of the head. Projected area of the head is a full circle. PRM to power 2, it's area. Okay? Then, I show it better. Projected pi r m squared is the actually area, projected area of the head, and pressure act on this area and produce at x direction, F external at x direction is pi times the area is pi pi r and mean square, mean radius r square. Then this is external force. Internal force is sigma longitudinal, which is times the area of the thickness, the strip, which this side is thickness, this side is 2 pi rm, And this area is 2 pi rm times thickness, the rectangle, times stress, 2 pi rmt, is internal reactions at the cut section. Then sigma fx equal to 0 says that sigma L 2 pi RML must be equal to 2 pi RM T, not L, area, must be equal to pi I pi RM squared. Let's cancel out these two, pi with pi, and then sigma L is equal to longitudinal stress pi rm divided by 2 thickness T. This is longitudinal stress. I write it here. Sigma L is equal to pi rm divided by 2T. Okay, we do not need this anymore. Let's consider for hoop stress. For hoop stress, just cut a ring from the shell. Cut a ring, imaginary. But here, for example, if I cut a ring from this shell and show it the ring is in three-dimensional, like that. And internal pressure act on it, and hoop stress, if I cut the ring in the middle, we can reach to hoop stress, which is in this thickness, We do not consider shell thickness at here. This is pi. And the stress act in this direction, sigma h. What is the length that we consider here? Consider delta L, small length. Then again, pi acting on the projected area of this half ring, which is a rectangular. Length is delta L, and length, width is delta L, and length is the 2 pi r m is the diameter 2 rm. Then let's write the internal and external forces. Internal force here is this L times T, L T. We have two areas, sigma H times 2 LT is the internal, which must be equal to external pi times this area, which is pi times 2rm times delta L. And here, the same as delta L here, can be cancelled out. And we got sigma hydraulic equals 2 pi IRM divided by T. 2 is cancelled out by 2. here, and pi r m divided by T. Let's write it. Sigma hoop stress is pi r m divided by T. Okay, let's look at that. The governing stress here for design is hoop stress. Hoop stress means circumferential stress is double in all cases, is double the longitudinal stress. And then let's draw a Mohr circle for these conditions, that one stress is double the other one, and we don't have shear stress at these conditions. Just if you draw Mohr circle, sigma I hoop stress, sigma L, then your Mohr circle is between them. That's a double. And what does it mean? Mohr circle, tau max is equal to sigma h minus sigma L divided by 2. This is sigma L. This is sigma L as well. The sign is sigma L over 2. That's a shear stress. Is it a condition? No. Why? Because we have another stress which is sigma Z that act in the direction of the perpendicular to the shear, but the value I told you there is no stress in this thin walled cylinder, and it is 0. 0 means what? 0 means that we have one stress here. And in this case, what happened? There is another Mohr circle between 0 and sigma h, and one between 0 and sigma L. If I draw it, not equal, changes during rotation. And then the real tau max is this amount. Because of z, sigma z, which is 0, tau max here happen, which is double of this tau max, and is equal to sigma L. And the stress at these conditions is sigma L. What does it mean? It means if we rotate this element 90 degrees in Mohr circle, counterclockwise, and 45 degrees in element case, if this is the surface face, right side face, then we rotate it 45 degrees, we rotate it 45 degrees, here, then this is the face after rotation of the element, and stresses on this element is positive clockwise tau, which we call the tau only, and tensile stress, which is equivalent to sigma L. This is also sigma L. In this direction also sigma L. Tau also here sigma L. And tau here, and tau here. Intensile sigma L here. Tau max here. Tauing L is not correct value, but I just wanted to say that stresses or value of the magnitude of these stresses, all of them is equal to sigma. Sigma is equal to sigma L and tau is equal to sigma L as the same. The value is the same. And then maybe this is the worst case scenario for designing these pressure vessels. Any designer must consider both cases. First, design based on maximum normal stress, which is equal to sigma hoop, and then consider based on the maximum shear stress. But maximum shear stress in this case is not this one in two-dimensional Mohr circle, but in three-dimensional Mohr circle. Consider sigma 3 as 0 and sigma z. We have another Mohr circle also here between the minimum principal stress and 0. 0 also is the actually minimum principal stress, not sigma m. But if you draw a circle here, this is complete Mohr circle for this case, which we call the three-dimensional Mohr circle. Then, designer must consider tau max here. And don't be aware of this value of tau max that is double the tau max that they expect. They think. Okay, let's consider code of ASME for designing pressure vessels. And see the ASME formula is from what source they get the formula. ASME formula, they designed actually for thickness because they know the material known. For example, for pressure vessel, they use SA516D, which is used, the plate is used for pressure vessels, and at 300 degrees centigrade temperature, allowable stress S is equal to 128 megapascal. And then that's the specification of the plate is in market they produce. Then you know the material, you know the stress maximum 128. Then if you design based on the, you know the stress, design is based for thickness. T required is Pi. Instead of using actually the mean radius, they use outside diameter or outside radius. And the difference between if you calculate based on outside radius with mean radius, less than 5%, doesn't matter. We stay on the conservative part of the design. Then RO divide by, because why I consider this formula instead of this, because hoop stress in cylindrical pressure vessels govern the design, okay, based on sigma hoop. Sigma hoop is the stress that reach to maximum fast and always double twice the sigma longitudinal. Then this T required T according to ASME doesn't end here. ASME says, okay, Pi are outside, but this sigma h is S, they called it S. They use the allowable hoop stress that can produce inside the material 128 at 300 degrees centigrade. But the problem is this. They weld after rolling the plate, they weld it at seams, longitudinal seam here. And if it completely X-rayed, fully X-rayed, completely radiograph, full radiographic X-ray. You can say, okay, I'm sure about the weld, and I take it as the plate, means the efficiency is 100%, or put E here, efficiency of the weld, which is 1. But if you just try testing some points, not all full length of the weld, efficiency can be less than 1, like 80%, 85%, 0.85, something like that. And they added a value which is not considerable value. For example, for cylindrical is 0.4 pi. Okay. Assume that we wanted to find a thickness for a pressure vessel that has a diameter outside 1800 millimeter, and inside pressure they use 500 psi, which is equivalent to 3.45 megapascal. Let's substitute required T should be 3.45 megapascal times 900 mm, radius outside 128 times 1 efficiency of the weld plus 0.4 times actually pi 3.45. And T required here, if you calculate that, it should be about 27. I think 20 for this one is 24 mm. Yeah. But many things you must consider in the manufacturing of this pressure vessels. And this is you must consider what? Because you are going to go in the market and order for this plate. And in ordering to this plate, you must know each plate is produced by mill machine. And there is a tolerance, plus minus tolerance for mill machine. For example, if you say that nominal size of this plate is 20, when you choose it and measure it, it is 17.5 mm, not 20 mm. This tolerance belongs to manufacturing machine, mill machine. Each factory to factory is different. Some factories says that plus minus 1.1 mm, 5 mm, till 40 millimeter thickness for the plate. Okay? But a standard ASME says, ASME section has 8 division 1, says that consider 12.5% for then. T nominal is equal to required T that we calculated from this formula, plus corrosion allowance, plus mechanical allowance, plus erosion allowance, plus mill tolerance. You must consider all of these. Not all design consider all these. It depends. For erosion, they consider that the following, actually the gas or liquid inside the pressure pipe as a pressure vessel is flowing and attack to the wall and erosion happen. But if the material don't produce erosion, no reason to consider erosion rules. Corrosion always is considered. It doesn't matter material is flowing or is still. Then to require this 24 corrosion, most of the time they consider 3 millimeter for corrosion allowance. For mechanical allowance, it depends. If you wanted the pressure vessels after fabrication, some material removed from its skin, outer shell, or not. If yes, you must add this value to this thickness. How much you are going to remove after fabrication or manufacturing. Here we don't consider anything for that, but maybe 2 or 3 millimeter. Not for this, not for, but mill tolerance, no, you have to consider it, 12.5%. Okay, we get here T nominal is equal to 27 here. How I consider mean tolerance? I say that. How much was the nominal size of the plate in the market that after reduction of 12.5% tolerance, it reached to 27? How much was that? I have to divide it minus my tolerance, which is 20.5%, which is 0.87. 27 divided by it actually is 30.85. Then you have to go market and look for plate which the nominal size is larger than 30.85 or 31 millimeter. In this case, you are sure that you consider everything for this pressure vessel. Okay? Thank you for watching and see you in the next video.